One thing we discussed when we first introduced statements is that often you can have a declarative sentence, P of X, but it has some variable. Maybe I will mention an example here. For example, P of X is the statement that X is even. And as written, you don't know if it's true or false. Well, because it could be either one, right? And so this P of X is not a statement in the mathematical sense because the truth value is ambiguous. Okay, this we have discussed. Okay, now we talked about and did practice making a statement out of this, which is you could just have a specific X. For instance, 2 is even. That's a statement, it's true. 5 is even. That's a statement and it's false. But another way we can make a statement is using quantifiers. We can create statements with a statement like this about X using quantifiers. And there are two main quantifiers. One goes like this and one goes like this. This quantifier is for all. And this quantifier is there exists. Okay? For all and there exists, symbol, word. These are the two quantifiers that we want to discuss. Now, for all, X, P of X. This is true provided P of X is true for every single possible X in whatever you're set. So you could say for all X in Z, P of X, or maybe it's understood you're working with real numbers, something like this. Okay? Now, this one, there exists X, P of X. Again, you're working with X integers or X in some set. This is true provided at least one. Provided P of X is true for at least one X. Okay? Now, it could be the case that P of X is true for every single X, and there exists X, P of X is still true. It means there's at least one. There could be 10. There could be exactly one. There could be infinitely many. There exists X, P of X is true. But the for all, the only time this is true is when the expression P of X is true for every single X. And here, if this fails one time, even, then for all X, P of X will be false. Okay, now, let's just, at the bottom, look at this particular one. So if I said here, if I said for all X in Z, X is even, or if I said there exists X in Z such that X is even, okay? These are both statements. We don't have this problem with the truth value being ambiguous because I added this quantifier in front. This one, for all X in Z, X is even, is a false statement because, of course, for instance, 5 is not even. There exists X in Z such that X is even. This is a true statement, okay? So let's do some more examples with these quantifiers. Here are several examples. First of all, they are all statements, right? With the quantifiers in front, each one definitely is true or false, and we will figure out which one it is. So the first one, there exists X in Z such that X plus 3 is 10. This is without a doubt true because, for example, just solve. We get X must be 7. Okay, so this, we just need 1. Of course, we could have more than 1, but for the there exists to be true, we need to find at least one integer that satisfies this. And in fact, there's only one, and this would move into the next one. For all x in z, x plus 3 is 10, is definitely false because it does not hold for every single integer. Then, for all x in z, x squared is bigger than or equal to 0. Yeah, this is good. If you square this is true even for more. We could put for all x in R, x squared is bigger than or equal to 0. If you square a real number, what you get is something that is non-negative. Okay, the next one, for all integers, is it the case that 3x is less than or equal to 4x? Well, this is okay if you have non-negative integers and certainly for positive integers, which is the next one, but for all integers, no, this is false. To realize it's false, we only need one where this fails, and for example, take x equals -1, which is an integer. -3 is bigger than -4, and so this fails for this one integer. The for all is false. Now here, as I was saying, if you have a positive integer, this is fine because, let's see, 3 is less than or equal to 4. And if you multiply by something positive, it does not change the inequality. So this is true. Okay, the next one is another there exists an integer such that 2x equals 3x. Well, yeah, this is true. In fact, we know what the integer must be. It is 0. We only need one for there exists to be true, and in fact, there is only one. We can conclude x is 0 here. The final one, there is an integer, x, such that x squared is 2. Well, we know the only solution is, well, there's two solutions. It would be square root 2 and negative square root 2. Neither are integers. So the answer here is false. In fact, we can say more. We can change this to q, and it's still false. This is something we will prove by contradiction later in the semester, that square root of 2 is not rational. But for now, certainly it's not an integer, okay? Now, nested quantifiers, and order matters here, as we will see. This is very important. But the nesting, and we will talk about nesting two quantifiers, is when you have some statement that not only involves x, maybe it involves two variables, say x and y. So there are 4 different types we will discuss. One is if you have for all and for all, and then you have a statement, okay? And then you could also have there exists and there exists, and then you have a statement. And again, when we're actually working with these, this will be in some set. So maybe for all x integers, for all y integers, like this. Okay, then there are two more. One, you have a for all first, followed by a there exists. Or you can have a there exists first, followed by a for all. Okay? And as I mentioned, order matters, and moreover, order is very important with these two in particular. Now, let's talk about each one of these. For all, well, this just says, this is true. It means P of x, y is true for every possible pair. I'll even say it this way, which would be in some Cartesian product. So this, in fact, you could say for all y, for all x. It's just, this is true. So this is true when this P of x, y is true for every possible pair, x comma y, okay? And similarly, this one, this is true when, well, you have one ordered pair, so there is at least one x comma y with P of x, y true. There may be more than one, there may be infinitely many ones, but there's at least one. X, y, really, you can think about it living in a Cartesian product such that when you evaluate this P at x, y, it's true, okay? So these two are, well, I think the easier two to think about. For all x, there exists y. This means the x comes first. For all x, there is a y, but y comes second. So y may depend on x. Here, there exists x such that for all y. Here, the for all comes second. So this says there is one x. It comes first. That works for every single y. Now, sometimes thinking about it like this is challenging. So let me use it in an example, and hopefully this will, well, think about the difference between these two. So let's see, for all x in z, there exists y in z such that x plus y is 0. And then here, there exists x in z such that for all y in z, x plus y is 0. One of these expressions is true, and one of these expressions is false. And this is why this really matters, the order here. Okay, well, which one is true, which one is false? This is the fun part of this activity. Okay, for all x, there is a y such that x plus y is 0. And I said the order matters. Pick your x first. Okay, so now you have x handed to you, but it's arbitrary because this needs to work for all x. For all x, okay, I have 1. Now find a y such that x plus y is 0. Well, this is fine. This is true. You can take y as minus x, right? You were handed x first. So you have it in your hands, and I say now find a y such that x plus y is 0. Well, you have x. Just take minus x and you're good, right? X minus x is 0. But this one is false because this comes first. So I need 1x such that no matter the y I choose, x plus y is 0. Well, that's not going to work. There's not 1x such that no matter the y I choose, x plus y is 0. Because, for instance, if I picked 1, that would say x had to have been minus 1. Now, is that going to work for 2? Well, no. Minus 1 plus 2 is definitely not 0. So there's not 1x. You see that there exists comes first, such that for all y, x plus y is 0. And this is really the difference between for all there exists versus there exists for all. The order matters here. That's quite important. Now, before I move on, we can, just as a nice exercise, we can answer this question with this x plus y is 0 being P of x, y here and here. We have different nested quantifiers. Okay, so what would we have if we think about this truth? For all x in z, for all y in z, x plus y is 0. Is it true? Well, definitely not. If you pick, this would say for every ordered pair, x comma y, and, well, z cross z. If you add them up, x plus y, you get 0. No, this is false. You can take, for instance, x is 1, y is 1. We get 1 plus 1 is 2, not equal to 0. This is a false statement. This one, there exists x in z. There exists y in z, such that x plus y is 0. This is true. Well, there are many pairs, but we just need one pair in z cross z, such that x plus y is 0. We can take x is 0, y is 0, for instance. So this is true. Or we could take 1 and minus 1, or 2 and minus 2, right? Any of these will work. Here are a few more examples where you can practice the nested quantifiers and decide if they're true or false. And all of these have one of the quantifiers is for all, one of the quantifiers is a there exists. So we're really gonna have to think here because the order, as I mentioned, it really matters. The first one, this says for all integers n, there exists an integer m with m bigger than n. So the for all comes first. So imagine I hand you a little n. How can you find an integer that's bigger than it? Well, this is true because we can just take m to be n plus 1, for example, okay? Because the there exists comes second, m can rely on n is fine. This is true. On the other hand, let's do the next one. It says there exists an integer such that for all integers, n is less than m. This would say there needs to be 1, well, or maybe 1, it's a there exists, but we need an integer that's strictly less than all the other integers. This does not happen. This is false. The integers are not sort of bounded below. But if I change it, you see everything in line 2 and line 3 is the same, except I switch this here. So this says there is an integer such that for all natural numbers, the integer is less than the natural number. Well, this is true, and this is one where you have infinitely many options. You can take n is 0. You could also take n as minus 1, n as minus 2, any of these, because the natural numbers are 1, 2, 3, 4, and marching forward, and any non-positive integer will work here. So there are many options. In particular, there's at least one. This is true. Okay, now the next two are fun. The next two have to do with subsets. So here we have, there exists a subset of the integers such that for all subsets of the integers, x intersect y is empty. Now the there exists comes first, so there needs to be one, or maybe there can be more than one, but there needs to be one that will work for every possible subset of the integers. This is true. This is true. What is this one? It's the empty set. So if you take x is the empty set, then, well, the empty set intersect any set is the empty set, because it would be elements that are common to both the empty set and y. Well, there's no elements there, so this would be the empty set. So this one is true. Now here, the for all comes first. So for all subsets of the integers, we can find a subset of the integers such that x intersect y is the empty set. Now, this is true. We can use the same one. For example, for all x, let's see, in this case, it's y is the empty set, okay? Just because it's the there exists goes with the y letter. But you could also, because the there exists comes second, we have more options here. So both of these are true, but this one you have more options. For example, you could take y to be x complement, and then x and x complement, they don't have any. We saw that in an example in our sets videos, but they don't have any elements in common just by definition. So in this one, you could pick a y that depends on x, but you could also pick this universal y that we used in the statement above, really. Well, now here is a great exercise. And the question is, are these equivalent? And if so, we should talk about why. And if not, we should give an example of a specific P and Q such that they are different. This one says, first you take the statement P and Q. Then you ask, there exists. So there exists X such that P and Q is true, versus there exists X such that P of X is true, and there exists X such that Q of X is true. So the and is in the middle of these two. Now think about this for a second. You could pause the video if you want to think on your own. It's a great exercise. The answer is no. These two are not equivalent. And the reason is you could have one x value working here and one x value working here. So this would be true, this would be true. You take it and it's true. But there's no sort of common x that makes them true at the same time. Now, that's a rationalization, I guess, but let's give an example. So let's work over the integers and let's look at P of x to be x is even. And Q of x is the statement that x is odd. And we are working over the integers. Meaning if I say there exists, I mean there exists x and z. Okay, so here, the left-hand side, there exists an x, so that both of these are true. This is false, because this would say there is an integer such that, well, the integer is both even and odd. No, there is no integer that is both even and odd. In fact, we will prove this later using a proof technique called contradiction, but we can certainly think about it now, just knowing that the even integers are 2, 4, 6, 8, etc. The odd integers are 1, 3, 5, 7, 9. Of course, we have negative ones too, but there's no integer that's both even and odd. So there exists x in z. P of x and Q of x is false. However, this one is true in this example, because here, for example, 2 is even and 3 is odd. 2 is even means, let's see, this one is true. 3 is odd means this one is true. And then we're just anding two true statements is true. So you see, this expression and this expression, they're not equivalent. Now, come here. This one, we have an and the P of x and Q of x, there's an and, just like above, but then it's for all. And here, for all, and then we and. Are these two equivalent? Well, the answer in this case is yes. Both of these expressions are true, provided P of x is true for every x and Q of x is true for every x. Because this would say P of x is true for every x. This says Q of x is true for every x. Then we have an x, so we need, then we have an and, so we need both of them. And similarly here, this would say, oh, I forgot my for all. This would say P of x and Q of x is true for every x. So they're saying the exact same thing. So these two are the same, these two are not the same. And my bottom line, or my words of wisdom here, is you have to be careful with quantifiers. Are these equivalent? I've added the answers on the board. We saw no for the first and yes for the second.